In case there's somebody out there I'm not seeing who's online, just to say I'm Ann McDermott. I'm in Columbia in the chemistry department. And in our research group, we do quite a lot of solids NMR, mostly on biological systems, mostly on proteins, mechanistic work. And I've been here in the back of the room asking strange questions. So we are going to start talking about anisotropic interactions. Anisotropic, not isotropic, spatially dependent, specifically rotationally spatially dependent. That's all synonyms. Does that make sense so far? That's what anisotropic means? It means it depends on how it's rotated, spatially dependent. And I'm going to see if I can get my cursor back here so I can advance the slide. Just give a little overview of what we're going to do in the first part, which might be today and tomorrow. We'll see how the pace goes. We don't have to rush. You know, you guys, especially those of you who bother to come in person, you can give me a little hint to slow down or speed up. That's fine. It's not going to be taken in the wrong way. So I don't know when we finish for one, but probably this week. So we talk about interaction that's important to the NMR experiment, like a chemical shift, that happens to be dependent on the orientation. And we're going to start using Cartesian coordinates because I think everyone is very comfortable with that. But we're not going to stay there. That's not our aspiration. And we're going to talk about like applications that are possible. Like, why do we care about this topic? How does it come up in real everyday or exciting science? So maybe somebody has a protein that they orient and they study the protein, they orient it and they study it. The people who do that, that's actually not what we're doing at the moment. Maybe understanding what I'm going to teach you helps to recognize approximations we make in NMR. And I think you can never take the advanced topics in NMR and connect them down to the foundation of whatever physics you took as an undergrad, unless you know where the approximations were made. So if I'm a little tedious or pedantic about, hello, welcome. If I'm a little tedious or pedantic about, that was another approximation over there, don't miss that. This is why, because I think all of you have the right to see the through line between, you know, Feynman's lectures on physics and the most advanced NMR. That's part of what we want to do. It's fun, among other things. So we want to understand approximations. We want to understand experiments that depend on orientation. And some of the tools we're going to need in order to talk about that are math tools. Like, they're not super advanced, but you might not have learned them before. And that's fine. And we're just going to review them here. Some of you already may have a strong comfort level with these, and maybe then you can help the discussion. Where we're headed at the end of it is to talk about some important experiments that we do every day. Magic angle spinning, right over there on the 750. We try to talk about those and how they work. But we have to take our time to get there, I think. So, up till now, we have been talking about the orientation of spins. Like the M, the vector M in this picture, which was supposed to be color-coded. It's sad, colors aren't there. But the spins, and they have an orientation. And the we here, the royal we is art, has been talking about the orientation of the magnetic moment, which, in my view, I take it as literally an orientation of a nucleus. In other words, that nucleus has other observables. And when we rotate the magnetic moment, those other observables demonstrably also rotate. Okay, so you've got an atom, it's doing its thing. On the inside, you've got a nucleus, a speck. It may be rotated. It may be subject to torques, to forces, to torques, and it moves and rotates, okay? And when it moves and rotates, we can measure that. That's what we've been talking about. So we kind of bypassed what was up with the molecule. We didn't talk about that. We just said, oh, let's play with this nucleus, right? Now we're going to address the fact that all the interactions that interest chemists in the spectrum, they're on a molecule. They're about the bonds and the electrons, right? like J and dipole and CSA, all of that's bonding. And we're chemists at some level, we like that stuff. It's also rotationally dependent. Not just the nucleus is rotating, the molecule too, and to a wonderful approximation, those are two totally independent operations. Okay, I can muck with the nucleus, I can muck with the molecule. It takes a different set of tweezers, it's a different thing, but they both may happen. So we have two completely different coordinate systems that we're working with at every moment in the whole sequence. So why didn't we mention this before? Why is this the first time it comes up? If it's like a really obvious answer, don't overthink it. If I ask a question, it's just for pace. Sometimes it's not really to quiz you. So don't feel like you have to overthink it or don't feel like you have to be right. But why do you think this didn't really come up yet? That we also rotate molecules, not just nuclei. And what does that mean? Why were they isotropic?
It's because it's
They're tumbling. They're not only spinning, they're tumbling. They are, because it's chaotic. It's a chaotic, random, no memory type process. But it's on a pico to nanosecond time scale. And by the time we even get a little bit of our pulse going, it's already averaged everything. Okay. So we didn't care because it was. So we have two sets of coordinates we're going to use in the problem. So there's a vector for B naught. That's our coordinate system. And when we lose our B naught, we lose our experiment. There's a vector for the nucleus, that's M, magnetization, and there's another vector for the molecule, which is typically like some bond, like we'll call that bond the vector of the molecule. Again, I'm going to cover the equations that relate orientation of the molecule to frequency measured in a spectrum. And so there's an equation, so you can look it up. So am I really going to take two whole lectures just to motivate one equation? Kind of, yeah. And the equation is useful for solids, magic angle spinning, which is the main thing we're headed for. Like, what are we talking about with magic? What's magic? It sounds pretentious. So what is this? Also, partial alignment of liquids. So, you know, residual dipolar couplings on top of J couplings. Also for studies of motion, red field theory, relaxation. So you saw Art begin to hit at these topics last week. And then it comes up with structural constraints for solids in lots of contexts. You need to put that description of the anisotropy explicitly into the problem to talk about the constraints. It's a different kind of question. I would like to point out that we are going to be using spherical coordinates, specifically for tensors, not just vectors. That notation is a really good way to describe the dependence of frequency on the molecular orientation. It's a good way to do it. So spherical tensor type coordinates and not Cartesian. And my question is, did you already use that for something else? Is that something you've done a lot with? Again, no right answers, no wrong answers. Not so much, good, because otherwise I'm wasting your time for 2 lectures. You used it a lot, like in some physics class for some other problem. Sometimes when you learn about the atom, for example, it depends on an instructor, but you might spend a lot of time in these coordinates and then, you know, you just have to be part of the teaching team for 2 days, if that's the case. Okay, well, I want to talk about homework. In, I think in the Dropbox that you used, because I gave it to Whitney yesterday, there are these slides and also a handout that follows it, but it's typed up. You know, it's like a sort of chapter length thing on this. And it has homework problems in it. These slides have a few questions. Those tend to be in red. Like if you see a red font, it means pay attention, or here's a problem for you to think about this week, or watch out, or so the red font usually is a kind of warning sign, and then there might be some problems in the slides that way in red, but mostly the problems are in that handout, and they are numbered up to like 14 or 15, and they're from previous years. I might add some this year, but right now I'm just pointing out that you have several that are assigned actually, give me a second, because I think I want to see if I can find a more recent.
The problem you want to assign.
I'm sorry, again? Say again?
Are you looking for the problem we decided to assign?
I'm looking for a more recent version of this PowerPoint. It had that and it had just a few other things. This is the PDF version. Just one second. It's all right. It's not so many improvements, but it's sort of weird. It should be. Slow. You know what? I'll take the offer, Anish. I'm going to modify this in real time. It's problem 7 and 9 for this week.
9 plus 3. He said 8 and 14.
Uh-huh. And look at them all. Try all of them at some level, but you only have to turn in those ones. Possibly one more TBA tomorrow. Next week, I mean. So by this, I mean do this week. Turn it in this week by Tuesday, March, what is it, the 3rd or? Next Tuesday is March 3rd, yes. The following week, so March 10th. All right, is that clear? Like a week from today, I want you to look at all of them, but I actually am only asking you to turn 2 in for feedback. Make sense? Let's share this again. That looks okay. All right, so I just want to say, you know, anisotropy is important for solution, is important for solids. You're going to see it come up in solution NMR discussions. But this, besides being the section of the class where we introduce anisotropy, it's also the section of the class where we introduce solid state NMR. And there's something I just want to say, maybe obvious to some of you, but there are a lot of similarities and then some distinctions between solids and solution. And I want to list some of the things that are salient from my point of view. So solids versus solution, what's the difference? Difference might be that overall tumbling is not happening. That is our functional definition of what a solid is, actually. It's nothing to do with pouring, melting, poking, all those kind of middle school definitions. It's really about whether the molecule is rotating. That's the whole. So as a result, there's no specific relationship between molecular weight and line width. That's not the driver of the line width. Other things make the line width what it is. aligned samples for solid state NMR can be studied. They get really, really big shifts that are not interpreted by databases of chemical functionalities. They are not interpreted by intuition. They are interpreted by angle, first and foremost. Big, big shifts that are about the angle. A lot of times in solids, the sample that we're studying, though, is not aligned. We call it a powder. It means you took something, it's a gel or a dry powder or whatever it is, you decided to study it, it's how it is. But now it's not oriented in any particular direction and it's not rotating. Therefore, all orientations are represented in an inhomogeneous distribution. Right? It's a population of different angles that are giving you different shifts. We'll look at a cartoon of that in a minute. But this word powder comes up a lot, and that's what it means. It means it's not going to rotate, so it's in an angle, but it's not aligned, so every angle gets represented, and we have to take care of each one of them in analyzing the data. For example, a ground powder crystals. That's why the word powder is because that was some of the first things that people said. Frozen solution, unaligned frozen solution. These are examples. And they're going to have really broad lots, and they're going to have bad sensitivity of detection. So it's not for the faint of heart. Also, another thing that's different for solids versus solutions generally is that the dipole coupling is not averaged by the motion, something we'll get into more quantitatively in a minute, but as a qualitative fact, that means you have these networks of strong couplings that go out. And I think they don't really like converge or end anywhere. So you'll see this vocabulary in all of the solid state literature from the earliest days till today about a bath. And it's like physicists talk for the fact that you're in a network of couplings and you can't tell me how many there are. They just slowly, slowly decrease, but it just, it's sort of unmanageable from a analytic, deterministic point of view. So we go into a different limiting picture where you have maybe a few spins, but they're always in connection with this thing called a bath, which is just a whole bunch of spins that are related, that we don't have a physics-based description. The bath, the network. You don't have to have that in solution NMR most of the time, and you have to have that picture in your solid state picture most of the time. So that's another qualitative good. Think about this. A geminal proton, 30 kilohertz. Vicinal and tertiary contacts are not that much smaller. They can be 10, be 5 or 10. That's a lot. Okay. If your J couplings were just like all over the place, 5 kilohertz, it'd be pretty hopeless in solution too. So what is that in comparison, by the way? I'm saying a network of couplings of that order of magnitude, where many are 30 and giant number of them are, 1 to 5 kilohertz. I'm saying that that's too strong. That's too many. But it's too strong compared to what? Nothing in NMR is like an absolute size of a number. What is it that in the back of my mind comparing it to when we say that? That's the problem. Mm-hmm. Well, that's partly I'm making a contrastive solution, so partly you're right, but also in the physics of the problem, it's getting compared to something else. Where the solution case is small compared to that thing, and the solid state case is large compared to that thing. What would that thing be? Well, it's going to have to be something else in your Hamiltonian, right? It's a thing in your Hamiltonian. I should only compare it to other things in your Hamiltonian. So what other things are in your Hamiltonian?
Shift interaction.
Yeah, and how does that relate to the couplings? We're trying to do what with it? Yeah.
Chemical shift interaction is much larger than our interaction, or was it all the way?
Yeah, so it is larger, and specifically, I just want to tweak your answer a little bit. Chemical shift difference. Like I say, I'm a chemical shift, I still don't care. I'm like, okay, that's part of the one, so what? But now I'm saying, okay, I have 4 or 5 spins and they are resolved according to their chemical shift differences. So those differences, we always compare those to the couplings. So let's say I have 2 spins and their coupling is super strong compared to their chemical shift difference. They are moving to the limit of indistinguishable particles where everything is non-intuitive, like the J coupling isn't there anymore, and all these crazy land things come out in A prime spin systems. So I'm sorry to tell you that solids, we live in that limit, and we do things to pretend we don't. Does that make any sense? Okay, because I didn't think it did, but I'm like, okay. So those are some of the things that are different between solids and solution. As this is our kind of intro to solids, let's talk about some things that are the same. Our broad goal, is to understand coherent evolution of the spins, the effective pulse sequences, to predict our observables, and ultimately to relate them to questions of biophysics. That's the same vision and goal, right? How are we going to get there? We're going to use a density matrix, a Hamiltonian, simplifications with truncations, with frame transformations, with product outlet, all that stuff, it still works. We're still using it. Okay, that's the good news. We still have the same basic tools to talk about relaxation. Not really very different. Redfield theory, Bloch-McConnell, stochastic layer, all that comes back again. And you know, some of these started in solids and got taken by solution. Some of them started in solution, got taken. It doesn't matter. All these apparatus, it's good. It's still, you can use it. The goal of determining structures from compact lists, like neighbor lists, orientations and anisotropic quantities, similar. Maybe a little difference in emphasis and methods, but it's a similar aspiration. How we get better structures is that we start to put orientations and angular things and portion angles. That we live in a world where our biggest challenge is line width, resolution, and sensitivity of detection. Same, we're in the same place. So in many ways, you're not starting over. I'm just adding things, okay? So that's my perspective on what the differences are and what the similarities are. So specifically, what do we do? The first thing we're going to do is introduce some anisotropic interactions. The next thing is, and don't be insulted, we're going to rotate some vectors. We'll start in a plane with Cartesian because the U are short. We're going to start in a place where it's like putting one foot in front of another. And we'll end up in a place where we can write with a set of indices and notation that give you a headache to look at. You're going to start to become confident with it, right? So we'll take it on step by step. What are we doing? Why are we doing all these rotations? Why are we reviewing our, algebra rotations? We're doing frame transformations for the molecule. Now, not the spin to be not the pulse to be not, but the molecule. So we have 2 parts to our Hamiltonian. We have this whole set of coordinates about the spin that we've been talking about up now. We're going to have in our Hamiltonian a whole set of coordinates about the molecule. Where's the molecule at that moment of the pulse? That description of where the molecule is, it doesn't depend on translation. It only depends on rotation. And we're going to be using frame transformations to say, how's the molecule doing now? Where is it now? Okay, and it will account for all the things, magic angle spin, molecular motion, which crystallite you chose at that moment, etc. That's what we need the rotations, the frame transformations to account for what the molecule is. That's why we're reviewing rotations. And we're going to have a hard look at why spherical harmonics can be better descriptions than Cartesian. The last thing I said on that slide is nested frames. So that has to do with the fact that there's not just one frame transformation usually. Usually, if you're accounting for 4 or 5 different things, such as molecular motion, crystallite selection, magic angle spinning, I don't know what else. The fact that there are 2 different interactions, so they're in the same molecule, but they're pointing in different directions, that's another thing. Each of those is a frame transformation. So in general, a complete problem not even all that advanced, just a medium level of advanced complete problem has multiple frame transformations. We call these nested, because first I correct for the fact that dipole and CSA is not the same direction. Then I correct for, oh, but I picked this crystal. Then I correct for, yeah, but it's halfway through its rotor period. Then I correct for, didn't you notice it was moving? I'm like, okay, these are nested frame transformations. So why is that important to point out is that we're going to be really interested in a premium on elegance in doing our rotations. We don't want to do it the dumb way. And that's why we need some patience in getting to the spherical harmonic. What we'll apply it to, magic angle spinning, introductory pulse sequences, and the treatment of partial averaging and motion. Those three topics we're aiming for in this segment of the class. We may come back later and aim for some other topics. Okay, optional topics that we may come back and may not. Simulation strategies, as in like the programs and how you approach it. Relaxation for solids, assignment strategies and pulse sequences, paramagnetic systems in DNP, quadrupoles, different kinds of quadrupoles, proton detection and what's special about that. Decoupling was added to that list, but I got the wrong slides here. And some more advanced theories. So I'm showing you this list because some of you out there on Zoom or here might have a favorite from that list, and you should feel free to talk to Anisha or me about. Don't want to learn that, and do want to learn this. These are optional topics, okay? Okay, so we start. That's the end of the intro part. Any questions about what we're going to do, or that intro, or motivation? All right, chemical shielding will be the first thing. Yes, please. Yes, please.
The assignment that you showed earlier, I wasn't able to get it. So can you share the slide later so that we can get assignment?
Can you see this?
Yeah, I can see the slide, but you showed homework earlier to be turned in on Tuesday, so I didn't quite get it.
Problems.
Yeah, thank you. I did share two documents on the drive, and I think they both have the problem correctly described.
Okay, thank you.
Thank you, and feel free to ask again.
Okay.
So chemical shielding, we're going to start with this. It's actually not the simplest. In a way, it's probably the more complicated of them, but I like to start with it. So in the NMR experiment, when we pay all that money and spend all that time with the care and feeding of the magnet, what we're looking for is something which is strong, constant over time, and homogeneous over space. It's beautiful. It's like a real piece of engineering. But at your nucleus, that is not true. It's not constant over time, and it is not homogeneous over space. But the thing is that that's where our information is. Because as the nucleus sits in a sea of electrons, bonding, non-bonding, and especially those with S character that penetrate the nucleus, close to the nucleus, that nucleus in a molecule is perturbed by the electrons. And the story usually is told this way, that the applied field perturbs the molecule and its orbitals, and those perturbed orbitals perturb the nucleus. And the best way to describe that perturbation is that the way the field perturbs the molecules is by changing the character of the excited electronic states, the unoccupied excited electronic states, that they mix a little bit into the occupied state. The first order perturbation, picture any field could, nothing special to the magnetic field. In fact, the magnetic field is a little weak on that. Electric field would have done a lot more. Okay, but if you put any kind of field, the field says that the electrons feel all of these fields act on electrons, and the electrons will feel differently in them. So whatever the solution to the Schrodinger equation was, the time independent solution, whatever it was in absence of the field, it's got to be a little bit wrong in the presence of the field. So our job is to understand the details on that. What is it that the B naught does to the orbitals to remix them a little bit? And then how does that remixing affect the nucleus? The best way to view that in my mind is to say, well, does it generate additional B fields? Because spin 1/2, and only spin 1/2, nucleus, his only boss is a magnetic field. He has no other boss. Okay, he doesn't care about electric field, which is kind of amazing since that's so much stronger, but he's just, because he's perfectly, symmetric with respect to that. He's not going to do anything electric field tells him to do. But even a tiny difference in a magnetic field will have a consequence. That's the funny thing about a spin 1/2. So the molecules perturb, and I think it is classical picture that the perturbation causes currents, but I think a better description is to say it remixes the orbitals, more general description. And those perturbations cause local magnetic fields, which are not homogeneous and not constant if the molecule is moving. All molecules are moving at almost every temperature. Not going to be constant over time, and it's not going to be homogeneous over space.
Yeah, okay, so I think you'll be talking about this later, but when you say remixing the orbitals, right, you are saying, let's assume a p orbital that's an excited state orbital. We are trying to mix the s orbital with this p orbital. Or?
If the s is what was occupied, yeah, I mean, her molecules will never be that simple, but yeah, right. If it was hydrogen or whatever, yeah. Yeah, literally, and it's just a little tiny bit of it.
So there's a probability.
Not per thousand, like a tiny bit of it, but it breaks the perfect, spin pairing picture. It makes ground states that little bit cardinal, that little bit paramagnetic, just a little bit. Now, the effect is small. It's a small effect. The mixing is small. The field is small compared to the applied field. And for that reason, we are very safe in assuming it's linear. It's not extra linear. Okay? We always teach a chemical shift is linear. It's only small, therefore linear. It's very small. The behavior of the nucleus, what it senses as being a torque, what it responds to as being a precession, is going to depend on the total field. The total field, not the applied field. So it will be B naught plus whatever this local response is. So B naught or B applied is homogeneous and constant. Local shielding fields are induced. The fields felt at the nucleus are induced by any kind of matter, molecules, local electrons. Doesn't have to be the orbital belonging to that nucleus. Could be something close by, another functional group close by. NMR frequency depends on B total. So omega is minus gamma B total. B applied plus B induced. Shielding, unitless, small, of the order of parts per million, linear, actually leading term, describing the induced field as a ratio to the applied. This is probably very, very familiar. This is very close to what you learned as a freshman or a sophomore. Just any questions, any comments about this? We can think of the shielding as being a partial derivative of the induced field with respect to the applied field. Already, you can think to yourself, I don't think that's a scalar. I think that's kind of dependent on orientation. What kind of a thing is sigma? Is it really a scalar? Like it doesn't matter which way I put the molecule or which way I put the field. Sigma, by convention, because for most diamagnetic systems, primarily diamagnetic systems, they're going to lower the frequency, lower the field. So we talk about shielding. It's proportional to B naught and subtracted. So most of the time when we are writing the Hamiltonian, we're going to assume that we are in a frame where we remove the main field. So like a rotating frame, like what Art introduced. So the Larmor frequency is subtracted out by frame transformation. So we can just talk about the shielding. We know B naught is there, but we don't carry it around in all the calculations. Okay, now this is really going back to your sophomore organic class, but I just want to make sure we're reminding ourselves about the following basic features. We have an arbitrary convention on where 0 is. That is not the native value of a naked nucleus, right? It's just like some compound. So we have a reference compound. And when we talk about chemical shift, not shielding, shift, we are talking about relative, experimental, practical definition. Is experimental compared to a reference sample and then divided by that reference sample. So there's a convention sample for every nucleus. Okay, and then there's so much jargon in this, and they have synonyms. So shielded or more shielded corresponds to lower resonance frequency, lower chemical shift, delta. Synonym to that is upfield, because if you wanted to get to the same frequency, you would have to jack the field up higher on the right side of the spectrum. Many of these things are flipped compared to any kind of sensible system you might have thought of. If I asked you to design this, you probably would have put 0 on the left, not the right. This is what we're doing. This is what you have to do. Okay. This list of synonyms is just best to memorize. People are going to talk about defielded, they're going to talk about upfield, downfield. And the sooner you feel like you speak that language, the better in reading papers. Okay. One thing to be aware of is that database prediction tools for chemists are strong, mature set of tools. So built into ChemDraw, some really wonderful websites out there, people who dig in deep on additivity laws that say, first tell me what your functional group is, now tell me what's next door, now tell me what your tertiary reactant can get it within 10. Particular for proteins seem to be a challenge, but the database is getting bigger, getting cleaner, the tools are getting better. ShiftX has been around for a long time and is a wonderful, wonderful tool, for example. Alongside those kind of approaches of just mining the data are physics-based approaches, quantum mechanical predictions of that very derivative. You know, the derivative of the induced B field with respect to the implied B field from first principles. And while in a restricted database, the informatics-based tools usually do better than a QM calculation, for most cases that I'm aware of. They don't give you the same level of insight, and they're not extensible to other functional groups. If you've got a new kind of compound, a new kind of moiety, then the database is diminished. And so there's certainly still a place for people doing quantum mechanical calculations. Now, all of that may have been said before and maybe kind of references isotropic shifts a lot. It's just a background to remind you of things you already probably knew. Now we're going to turn to what we're supposed to be doing today, the fact that the chemical shift is anisotropic. So you have a molecule that is not isotropic, okay? It's not a hydrogen atom. Then it has maybe no symmetry or some low symmetry. And the response of the field, the response of the molecule to an external field, the response of the molecule in the form of generating a new B field, it's its response to an applied B field, isn't isotropic, and so you have to specify geometry when asking that question. Imagine you're going to do it in a quantum mechanics program. You've got to place the field in the molecule in some direction. So the applied field is a vector, and we call that rank 1 because it has only one spatial index. Okay? And the molecule you could describe in a coordinate system with only one spatial index. But if you're talking about the response, you need to make reference to where the molecule is and where the field is. And that is a tensor, rank 2 spatial indices, 9 independent components. Let's just enumerate them. Let's say I got a benzene ring here. How does my benzene cast a field along X if I happen to put the field along X? That's the question asked by that element. How does that molecule generate a new field along Z if I happen to place the field along Z? Those are two different questions. But I don't have to make the measurement and apply the field on the same axis, so I can also ask, if I apply the field along Z, how does the molecule respond along X? It's a different question, and it's quite valid. An applied field along one axis gives rise to a response field along all three directions in principle. Could happen to be 0. All right, so here's a picture in the bottom left for a functional group that lacks symmetry. And we imagine that we put the field along Z in that picture, which is chosen to be the perpendicular of the aromatic plane, and that we make a measurement along X, which is chosen to be the bisector of the CO2. That's it, one element out of 9. 9 questions we can ask. Every other direction is going to be a linear combination of one of those 9s. This is a linear system, it's a linear response. We can use tensor mathematics then. I want to see something here. The induced field is a vector. Induced field is a vector. And it's calculated by combining the applied field and the response tensor of the molecule. So remember that response tensor, sigma, was the derivative of the local field with respect to the applied field. So it makes dimensional analysis sense that if I apply the perturbation, namely the external field, onto that derivative matrix, I should get back the response. So we're in a small perturbation limit. So the induced response from the molecule is the applied times this response tensor. So what's the applied? It has an X, Y, and Z. What's the response? Sigma, and it has 2 indices. And what do we get back from the molecule? This is a row vector with 3 elements. Would be easier to read if you had a compass here. These are the three elements. This sum, and this sum. So you get a response field, the 1/3, by combining 1/3, which is the perturbing field, onto the tensor that describes the generalized response function. Now, this actually is exactly the same as something you might have encountered in a different kind of class, in maybe a class in physics on fields and waves, or a material science class. This works just the same way as stress and strain tensors work. An external force is a vector. You poke on it. Which way do you poke on it? X, Y, Z combo. The response could be in all three directions. If you have jello and you push this way, squeeze out that way, right? That's normal. So the response to one component is in all three physical directions in principle. So then you need a tensor to keep track of all of that. The distinction being stresses describing internal force per unit area, strains describing the actual displacement that the material exhibits. So two subscripts, one to describe the perturbation, the other for the response. This is the same. This is the same as stress and strain, if you ever studied that. Now, we can simplify this. We don't actually need 9 things if we can make choices about our coordinate system. Like, maybe the field is just along Z, and we can just call it our convention. That gives us so much less math to do. So the induced field then becomes the product of the applied field times the stress or shielding tensor. And it has 3 unique entries, but we don't have to calculate 9 things. Everybody see that? That's just a frame selection using the major field axis, using Z. Now, here's another simplification that is completely distinct from that one. Though the response fields, and I'm going to add that word here just to make it more clear what I'm saying. The response fields in the molecule, its response, are induced along all 3 directions, right? The response field has 3 entries, and actually they're the same order of magnitude. They're not like, but a priori one's bigger, the other ones are small. That's not. They're all about the same size. Same with that stress and strain picture. I poke on the jello, it squeezes by so much and grow by about the same amount. It's like a volume conservation I'm using intuitive, right? So the responses along the 3 directions are same order of magnitude, they're definitely there, all 3 are there. And yet, when we do NMR and we're calculating the frequency, actually, we're only interested in the Z component of the response. Let me just make that clear by going back to the last slide. This is already so simple, but now I'm making another assertion. All I really need is sigma 3 for UV naught. That's all I really want. So I had like 9 different calculations, and I'm saying, yeah, I don't need that. Why would that be true? Why am I not keeping track of the response field of the molecule that it's actually generating a little X and a little Y as well? Any reason? We've seen this, that we only have IZ type Hamiltonians, but why? Because we're allowed to do that. The problem is we're allowed to do that 95% of the time, and then 5% of the time we say it's nonsense. So we have to be very clear. What is it about? Yes, please. Somebody speaking.
Is it from the B naught field being the source of the magnetic fields along the Z action direction, and that the X and Y components, second order that feed back, can be ignored?
X and Y components can be ignored. So there were two parts, Gregory, to your answer. One was that BZ is only along Z, and that's the first thing we did here. We said, we don't have anything in these two entries, right? B applied has nothing on X, nothing on Y. That simplified us down to just 3 calculations. I'm making a further assertion that we actually only need to do one of those. So B naught is along Z, and now we're only going to pay any attention to things that are along Z. This is an example, but both of the answers I got are very close to what I think is important here. This is our first example of a truncation. Truncation means confidence in discarding terms. So the total B field is going to be a vector sum of the field from B naught and the field from the molecule. It's a vector sum, right? So with the vector sum, you add components that are parallel, you add them with regular arithmetic. Just add them. But if they're perpendicular, you add them the way we learned from Pythagoras. So you're going to add the squares and then take the square root, right? So it's a vector sum means that B naught plus BZ, yeah, you keep that BZ, absolutely. B naught plus BX, it becomes a very safe approximation to get rid of it very quickly. Because you're adding as a square and taking the square root. So the magnitude of B is the square root of the sum of squares of the components, and that is a really, really good approximation as being BZ. Chemical shifts are parts per million. So it's just because it's small and it's a vector sum. It's that simple. It is true that the precision is slightly tilted when you're dealing with a molecule. It is slightly tilted. But it's not really of any practical consequence in general. The tilt angle is too small to be interesting to us. And that's doubly true for solution where you are averaging over all orientations, but it's also a good approximation. Does that make sense, everybody? So I have one of those red problems here that's like, it's not an assigned problem, it's just a thing to provoke you to think in the notes. We're assuming that By and Bx from the molecule's induced field don't matter. If you want, on your break, you can calculate the effect on the frequency in the lab frame, assuming that the induced field along X is about 100 ppm. That's big, but not gigantic. That's like an aromatic functionality for carbon, that kind of thing. So you got 100 ppm. So I apply B naught. I got my molecule. And I'm saying, yeah, let's just pay attention to the part on Z, just because she said so. But in the back of your mind, you know there's 100 ppm going sideways. And I'm saying, yeah, that angle is going to be something. Don't worry about it. You just calculate it. It's just Pythagoras. So you can do that on the right. You can tell me if you agree. Now, second question. The RF field is orthogonal, or it should be. The MAS probably a little bit off, but it should be orthogonal. And it's also about 80 kilohertz, so it's about 100 ppm too. Well, we don't ignore that, do we? We don't ignore our pulses. I'm ignoring the X component of the molecule's response. But we don't ignore the X component of the pulse. Why? Why not? Does the question make sense? Yeah, thank you. So I just said, I asserted that the molecule is going to have about 100 ppm sideways, X component B field, that it will be casting, and that I encourage you to ignore it. right? And you have some arithmetic you can do to form your own paint. Then I said, you know what? That X pulse is also in the same direction and the same order of magnitude. But I do not encourage you to ignore your X pulse. Why?
Well, we are applying X pulse in order to generate resonance, or like that should be in resonance, so that should affect.
It's on resonance. That's it. That's the only distinction being made. The X pulse from the molecule might be quasi-static. Might be quasi-static. The molecule is a solid and we're spinning so slowly, and the mass is not that fast, maybe. It's not on resonance. The pulse is designed to be on resonance, and if it's even a little bit off resonance, it doesn't do the right thing. All right, so does that raise a third question? Could there be a scenario in which these X components from the molecule begin to matter? Can you imagine? Everybody follows what Krishna's answer was, right? That X pulse is designed to be on resonance, which means that it follows the action of being on. Stays in the rotating frame as being a constant X. Whereas the X from the molecule, when we go into the rotating frame, it's like chaos, it's like going super fast, it doesn't do it. That's the magic of the rotating frame. It helps you focus on what matters and what doesn't matter. All right, so the molecule's X response. Do you think there's some loophole where it does matter?
So it might induce some transitions
If what?
if the frequency of the perturbation matches the energy of the function.
When might that happen? What's that perturbation? The molecule's response. You're saying
Lower frequency.
it might not be constant. But why isn't it constant? Why is the molecule's response not constant? If what?
Purified fields.
Might be if that, but that's too hard to do, but yeah. But why else? When might the molecule's response matter?
The rotation of the molecule has the induced fields are different when the molecule is rotating.
And what if that rotation had a component that made it be on resonance? And so how fast would that molecule have to be rotating? On the Larmor frequency, is that reasonable? That's the Larmor frequency for most of our experiments. Megahertz, like 100 or 10 or 1,000. So that's a time constant of 10 to the 8, 6, 8, 9. Who moves that fast? Small molecule tumbling in solution, maybe even macromolecule tumbling in solution, and how about functional groups? Which functional groups can get up and go that fast? They're a little slower than that, but yeah. Yes. So that's a relaxation process. That is the loophole by which X. So we ignore it for calculating shifts, but we pay attention to it for calculating relaxation, the X component of the molecular result. All right, so but if we're just going to calculate shifts, what we said is induced field, which we need to get the shift. That's what we're calculating, shift. You take an applied field onto the response tensor. And that whole thing approximates to only being sigma 3,3 D0. That is for a molecule sitting still in an arbitrary orientation. It's not sigma iso, it's sigma 3,3. 3,3. What frame are we in? Well, you get to pick, you'll see that later. But if nobody says anything, I guess the principal axis system of the molecule, like where X is the bond you like. Okay. Now, if you want to do NMR, you're going to use that field, applied field, response of the molecule, and you're going to put back in the spin degrees of freedom, Ix, Iy, and Iz. Those are measurement operators. And most of the time, we're just going to measure along Z. So we perturb along Z, we measure along Z, and we are sensitive to the 3. Just pick out that 3,3 element. So it's opposing geometry, both from the point of view of perturbation by the field and the point of view of where we do the measurement. We're measuring along Z. So the omega for our chemical shift is gamma BZ sigma 3,3. You only calculate that one entry. Just to summarize, your total Hamiltonian so far is a Zeeman Hamiltonian and a CSA, and that is giving you an energy splitting that's sensitive to B total, 1 minus sigma B applied. Your resonance frequency, you just divide that by Planck's constant. And in order to calculate that, including the perturbation, you pick out just the 3,3 element from the chemical shielding tensor. So molecular orientation is important. The actual value of sigma 3,3 depends on how you oriented your molecule in the field. B naught is always perpendicular, is always, the magnet. It's the magnet, and it's usually perpendicular to the floor. Could be parallel, I guess, for unusual geometry, but it's the magnet. And the question is, how did you place the molecule in that field? Here we're again showing one where it's perpendicular to the aromatic character of a carboxyl group. And so the frequency is going to depend on that orientation, selection of that orientation. So if a tensor is known in a molecular frame, we know the values in a molecule's frame, tabulated, given to us by the literature. That may or may not be the way we placed it in the magnet. And this is the frame transformation that we want to learn to do. Somebody's writing sigma, giving it some values, they gave us a sigma in the principal axis system, meaning when Z is perpendicular to the aromatic, so we have some value for that, and then another one when it's along the bisector of that carboxyl, and another one for that third direction. So my carboxyl, COO, Z is like here, X is like here, and Y is a neutral. X is here, and Y is some neutral perpendicular way back there. And so it should. So thank you. Yeah. So that version of the tensor is tabulatable. Somebody might know it from a calculation or a measurement, And they can put it in a paper and we can all share that information. That when I point this way in the molecule, I get this amount of shielding. When I point this way, I get this amount of shielding. But now I need to know how to do a frame transformation so that if I choose to put B instead, like perhaps today B is over here. What do I need to do to calculate that? That's what we're working on, okay? That's the frame transformation that we need to do. So it'll be written, tabulated, computed, measured in the molecules frame, the so-called principal axis system. You need a frame transformation to predict your experiment. Everybody good with that? How did we get these values historically? This is a very nice paper that involves Ruth Stark, Bob Griffin, and a number of other people, another era for NMR that is foundational to everything that we believe about solution in solid state NMR. A single crystal with excellent coordinates and determination of structure and everything is mounted on a goniometer, non-magnetic goniometer. So that means you have control over the angle and the rotations. And then an NMR coil. That's actually kind of complicated if you think you have to build that probe. How do you get the goniometer to work perfectly and still get a decent coil around your sample? Anyway, now you need to control the goniometer from outside the magnet. It's like old school peak out. It's pretty good. So rotate the crystal and along each of two independent axes and plot the frequency that you see in each spectrum. And you would get these beautiful plots. Very nice. And if you look at the spectrum and you start using your modern brain to say, oh, that's got to be the carboxyl group, that's got to good luck, because it's not necessarily sheet. They're swinging all the way through the spectrum. You have no idea who's who until you get the full plot and make the average. Okay? And when you're done with that, if you're good at these frame transformations, you get to report to the world the shielding tensor in the principal axis system. That's what you get out of it. Now, I really do trust the quantum mechanical calculation. So if I had a new functional group, I wouldn't do that again. I love those papers. I think it's really important that somebody did it at one point. But nowadays, if I want a CSA, I will trust those calculations, but really read up on what people worry about with the calculations, like how much vibrational averaging should we do? What is the right way to shift to a reference compound and things like that. They get the values, but with not very much motional averaging. So sometimes they're a little too broad. They get the orientation of, like the directions very, very, very broad. Now, sometimes what we have in a powder experiment is very different from that goniometer experiment. It is a histogram of all orientations ground up, sitting together in your sample folder. I mentioned this at the beginning today, and now I'm coming back to show you powder pattern, cartoon of a powder pattern. It's cartoon because I want to emphasize the orientation dependence by using a heat map of a rainbow, where there aren't very many that are in the North Pole. They're deep purple, so they're giving a very specific frequency, but they are few in number. So it's a low intensity end of this line shape. Then there are many, many ways to be at the equator. A lot more phase space there. The phase space, you might realize already, scales as sine theta. So when you're up near zero, theta is zero at the North Pole. There's very little phase space. When you're down at the equator, it's 1. And so that end of the spectrum is tall. So it's characteristic powder pattern line shape. One of the features of this cartoon is that I'm assuming that X is equivalent to Y. That doesn't have to be true for a real molecule. Acetylene would look like that. Nothing in a protein. I name one thing in a protein that's really uniaxial. What do you think? Anything uniaxial in a protein? Next time somebody tells you something is uniaxial in an NMR paper, just forget. Question. Is there like just anything? Uniaxial in the protein. So methyl group is close. But you know, they all have a barrier to the rotation. So what is that? That's somebody poking them from one side. And it could be not steric, it could be electronic, because they have a bond down here or something. But they're close, they're about the closest. All right, so molecules, coordinate frame. Turns into an angular dependent frequency. And if you assume there's no motion going on a molecule, it's like a histogram of frequencies. Yes, in homogeneous run.
Sorry, I just wanted to clarify that I'm understanding it correctly. So when you are saying you have like a large number of phase orientations that are working around the equator and very small number of orientations along this North Pole. I find it difficult to understand, like, how are we saying that there are so many different orientations in the equator compared to the
area. Like the area of this little purple thing and the area of orange
Oh, and the intensity is
proportional to area because equal opportunity to be any of those orientations according to area. I don't think there's anything else on this slide. Now, if there's no motion and there's no magic angle spinning, you are green, you stay green. That's it. You're just sitting there in the spectrum. And the width of these powder patterns due to CSA is like most of your spectrum for most of the function. Like you covered it. And so there's no resolution of one carbon from another. The carbonyls would never be distinguished one from another if we had to expect that. So what you would do, or what I did do, you introduce one isotope per molecule. That's it. You get an isotope. Like where do you want it? And it's not that easy to make that sample. And once you make that sample, that's a lot of signal averaging that you typically do because the line is so broad. Not because there's only one thing labeled, but because the line is so broad the way you're doing this signal average. I think the spectrum would be a few days, just the one spectrum. And we did that. Okay, so the symmetry of the chemical shielding, we were just debating the methyl group, which was interesting. The symmetry of the chemical shielding does reflect the symmetry of the molecule and its orbitals. So those situations that are spherical in their electron cloud won't happen in this one. You don't have it. You had argon and NMR, you shouldn't have this, except imposed by the box you put in it. If you have CO2, which we hope to have, you might have one of those rare cases of something that's strictly uniaxial, except for how it's hydrogen bonded onto the protein, right? Or maybe it has a covalent bond onto the protein. Now it's not uniaxial at all. Does that make uniaxial means there's a Z, but X is the same as Y. The opposite of uniaxial is rhombic. It means X and Y and Z are really unique. Each one of them is unique. Okay, so something even like a double bond instead of a triple bond will have three separate directions. Most functional groups in organic chemistry will have three separate directions. Will be rhombic. Okay, this slide is boring to read and also essential for conventions. Yes, Anish.
I just remember from some literature, that arginine, the zeta, Isn't it true that dicarbon is somewhat close to uniaxial? Okay.
It's in a plane with 120-degree bond angles. So, all right, obviously perpendicular to the plane is unique, right? We don't have to think about that. So the question is, if you have 3 equivalent bonds, isn't this direction different from this direction? Maybe it could be close. Maybe it could be close if the projected, if you think of the projection. It doesn't really have axial symmetry, that molecule, does it? It is the,
Maybe guanidine by itself will have
maybe.
symmetric, but
That's an interesting case. So you're coming up with these threefold symmetric things. I mean, it could calculate out to being very close. It could be.
yeah.
We should look at that. I wanted to talk about conventions. Because there isn't only one. This is awful. Okay, so the power pattern, if it's not uniaxial, if it has 3 distinct directions, which is the typical case, you will have 4 interesting places in that power pattern to note. And there's a derivation of this line shape that I could do, but I didn't. I don't think I did do it, and maybe it's in the notes and not in the PowerPoint. I don't think. But you could say there is the most de-shielded, the most shielded. So the edges of the power pattern. You could say somewhere in there is the isotropic average. We'll talk about its properties more later. But there's also a maximum of this whole pattern. And it's neither, it's not uniaxial, and it's not the de-shielded, and it's not the most shielded. It's another place, it's the maximum. And it turns out that in a general case, that is the mutual perpendicular. So that's the third Cartesian direction in the molecule, is that maximum. Something we could prove, but I don't have the proof right here. All right, so those are 4 interesting places in the power pattern to note and to label. And it turns out that that average, the isotropic, is actually just the average of these 3 numbers. Convenient. And the convention, the part of this that's conventional is that delta 1,1 is the largest number, the most parts per million, in other words. And delta 3,3 was by convention. Now, there's another way to label these. The Haberlin convention, you can encounter also in the literature, which is the unique axis is always Z. It will be the farthest from the isotropic, where X and Y will be a little closer to each other. So they are the plane, and this is the pole. Okay? Now that Z could have been on the other side. It would still be called Z. Whoever is the farthest from iso is Z. Okay? And another thing in the Haberlin convention is that, of course, it's still true that if you take X, Y, and Z and average them, you get the isotropic. Z is the farthest possible from the isotropic. Another thing is that you use this delta delta, which it can be seen in a lot of literature, solution or solid. And you call that the anisotropy. So delta, just little delta here, which is sad that we're reusing a symbol that we already used for something else. This happens. delta is ZZ minus ISO, so it's a measure of the width of the tensor. Whereas delta delta, which we see more often, is 3/2 of that. Why? Why are we talking about 3/2 of that? Because if it had been uniaxial, this is in the land where everybody wants to impose uniaxial behavior, then these two would have been at their average and fall. And delta delta is the distance between that fixed in this place. We're making an approximation of uniaxial and this. So it's like the whole span of the tensor, if you like. Okay. So delta is V minus ISO, and delta delta is 3/2 of that, as if it had been uniaxial and visible. Now, we take a step back a wee bit, but it wasn't uniaxial, and we say, okay, let's talk about how far X and Y are from each other. Maybe they're not so far. We'll make a number out of that. That number is eta. It's this guy, X minus Y, but fractionally, so it has no units, X minus Y divided by delta. So it's like, as a fraction of how wide this thing is, really how different are X. It is unitless. What do you think the units of delta might be? It could be ppm. It could be quoted in ppm. Or sometimes you want to think about it in hertz. That would be by specifying your field. Okay, those are conventions. Now, I'm going to, I think, let you have a break now. We've been going for how long? An hour and a half, right? Almost. And I'm just going to stop with a motivational slide. This is a segue to where we're going. This anisotropy in liquids for our spectrum is just averaged. You're just measuring isotopic. For static solids that are not oriented, very broad lines that are essentially impossible to fully analyze. Our next goal is to understand how that anisotropy behaves if we do this experiment called magic angle stick. So that's going to be our next target. And in order to talk about that experiment, because it's a very empowering experiment, we will be talking about how to write those angles and those frame transformations. So that's our next thing. I just want to say that while it's attractive to say you just want the narrow lines, so just dissolve it, there are reasons to think about the solids experiment, not just if your sample is more authentic as a solid, but maybe just for the information content itself. And for that, I gave you one example from a student from many, many years ago, and other folks in the NMR community, that if you think about chemical shifts as being interesting because they tell you about local interactions such as hydrogen. The information you get out of the isotopic shift is one number. The information you get out of a full tensor analysis, as you can do in solids, is 3 numbers. 3 is more than 1. Sometimes it's a lot more than 1. Because here's an example of a database of carboxyl groups and the 3 tensor elements laid out on a spectrum. And then each line here, rastering from the bottom to the top, is a different compound. The isotropic shift is nearly invariant all the way through. Okay, but so much information up here. These are carboxylic acids. They have their proton attached. Down here, these are carboxylates. The proton is off. And there's daylight between this 250. Is it above that or below that? Tells me right away, it's proton on or off. I can't read that from the isotopic shift. I cannot. If people look at a carboxyl acid and they say, I think it's deprotonated because of its chemical shift, watch out. That's not true. Down here, this should be invariant throughout the whole database. And if it isn't, it tells you that there's motion. It's really handy. So if it is motion, then I better watch out with my interpretation of this. what is this telling me about? Is a continuous behavior from deprotonated to protonated is the strength of engagement with some other functional group in the form of a hydrogen bond. That makes the deprotonated look almost protonated, or the protonated look almost deprotonated. So it's like there's a story in each of these three, and when you go to measure the average, there's nothing. Just like average, just doesn't change, immutable. So three can be a lot more than one, not just a little bit more than one. So there's a good reason we want to see these tensors. This is another study that is a database of proteins looking at the backbone gamete and how certain tensor elements are very responsive to hydrogen bonds versus others. This comes from the work of Tatiana Polanova and Angela Gronenborn. This is the C alpha and the tensor elements telling you so much more than an isotropic shift. This comes from the work of Chad Rienstra and Ben Wiley when he was a student there. So you can want to have these tensors even if your sample would have dissolved for you. It's possible to want them for that reason. Also, don't forget that the tensor does allow you, when you study an oriented sample, it does allow you to ask the question, what is the orientation of a particular functional group within this oriented bilayer, just by reading out that frequency. So just the tensor, as chemical shift tensor, can be a powerful, powerful structural constraint, but it's not a neighborless, it's an orientation. Great. So these are reasons that, even if you could get more beautiful line widths by dissolving your sample, you might at some point want to access the tensor information of the CSS. So we're going to take a break and come back for either more of this or a problem session. But either way, we're going to continue and do a little bit more rotation math tomorrow. Thank you. Okay, my Anish. I have a question. Eric Keeler. Yeah? You find out anything interesting? The crab.
The protein, the flat.
That broke. Listen, do you have some problems you want to do?
No, I just noticed that you haven't gotten to oil angles.
So I was thinking we take a break and keep going.
Yeah, sounds good.
Yeah, are you sure?
Yeah, absolutely. And tomorrow, depending on how much time you have to spend with your guests, you could do like 30 minutes of
Problems. And then I could perform in the right.
yeah.
That's nice. Oh, I really like that idea. Thanks for offering. And I'll just eat a carrot and then we'll go with it.
Yeah, I'm now curious to just fact natural abundance, humanity and nothing.
Natural abundance.
Yeah. Back into a rotor and
Yeah.
you can see what it do. I
Well, we
could
can also do a calculation,
yeah.
Also,
Probably it's pH dependent.
Well, it should be. Right, when you lose that. Okay, if you had three strictly equivalent bonds at 120 degrees, what do you expect? Do you think of it just as being a projection of, electronegativity and distance and a projection. If it's really C3V, is it really going to turn out to be UNX? So I think you may be right. Even without motion, no motion.
Carbon, just carbon.
Okay, has everybody who wants to stretch their legs stretched them? Everybody ready for a little coordinate systems? Anybody want to open up with a question? All right. Here we go. The Hamiltonian. What does it give you?
Directions.
What kind of quantity? What is it? An energy. And it should have no preferred coordinate frame. It is not a vector. It's a scale. It's just a number. 5 kPa per mole. Done. Right? It has no preferred coordinate system or frame. But when we calculate them, all of the ingredients for the Hamiltonian have to be put in a frame. Right? We don't have any other way of writing the CSA business but to choose a coordinate frame. I don't know how else to do it. Vectorial spin operators, fields, description of a molecule, it needs a coordinate system, but the Hamiltonian doesn't need it. So we're going to have all these indices and they should all go away by the time we get the energy back out. Hence, for describing the molecule's susceptibility is easiest to write in the principal X system. And it's easiest for me to share it. If I calculate it, I'm giving you that, I should write it in the principal X system. And I should tell you Z is the NA font. Right? So in a coordinate system. The applied field and the angular momentum, you should write them in the laboratory frame. Those are not the same things. They're two different sets of coordinates. Can we write an equation where we're like flipping between two coordinates? Not really, but we're going to have to try. So chemical shielding values reported in the principal X system. Sigma 11 is 240, sigma 22 is 170, sigma 33 is 105. We get them in those ways that we talked about already. From a guess, from intuition, from comparison to another compound, from a quantum mechanic calculation, from a compilation in a textbook, from Ruth Stark's beautiful data. Okay. Now, coordinate system, reference frames. My Hamiltonian for the CSA is minus gamma, B naught in the lab, I in the lab. Then I have to have sigma. I might want also to say I have sigma in the PAS because that's the way it was given to me. Then I have to have I in the PAS and B in the PAS. But what I cannot do is stupidity is if I put B in the lab and I in the lab and sigma G. It's not an equation. It's ill-formed. So we rewrite the vectors B and I in the PAS frame. And we have to use rotations to do that. So we move the vectors B naught as it was in the lab to figure out what is that in the PAS. It's a rotation. So let's just take a step back. You rotated things before, and I don't know how far you got. But for me, even though I've done a lot of this before, sometimes when I'm reintroducing myself to the topic, I like to start again. I've got a vector in 2 dimensions in a plane. It's just X and Y. It's just in the XY plane. I'm not even going out of the XY plane. And I want to move it. I'm going to move the vector through an angle. So I have a vector, V, and V is just an X component and a Y component. That's all. It's just like 2 numbers. I need to rotate it through an angle and make it a new vector. Okay, it's over here, I move it, kick it. All right, that's active angle change, active rotation. I'm actually moving it. The coordinate is staying still. This rotation I can write as a function of theta. R is this. Concretizing this for you. So if V is X, Y, and V prime is X prime, Y prime, what I need to do to V to turn it into V prime is multiply it by this matrix. Now, do you agree with that matrix? Please take 1 minute. Just take 1 minute to see if you think I just gave you a mistake. Consider a simple example. The vector is just along X. So the vector is equal to 1, 0. No Y, just X. Now rotate it by 90 degrees around Z, R sub Z of 9. So fill in R for 90 degrees. I mean this literally, get out a piece of paper, just do this. And tell me what the final result is. If you do this, you are confident with matrix multiplications, and you are happy with my definition of R. And then we can go to the next slide. It's an active rotation, so it's an active student. It's okay? You're happy? Okay, can we go on? You'll find a mistake. These slides have mistakes. I'm a mistake person. It's okay. So row vectors are different than column vectors. That was a column vector. Sometimes we have to write a row vector, sometimes we have to write a column vector. Like if we have B operating on I, one of them is a row, one of them is a column. We might have to rotate either one of them or both of them. How does the row vector work? If I have a vector U, prime is not, and I want to turn U into U prime, I have to also multiply that row vector U by R. But it looks different. I kind of felt more comfortable with the last slide. Now this is kind of weird because I put U first. I'm sorry, I should not say U prime here. U, and then R, and then R is actually the flip of what it was last time. Oh, if R is this, what is R inverse? Yeah, and here's the thing. R inverse in this case is the same as R of minus theta. So you could just fill in minus theta for being theta. Or you could literally take the inverse of that matrix if you remember how to do that. Okay. If I have a row vector as opposed to a column vector, I post multiply by R inverse. When we add a column vector, we pre-multiply by regular old R. Now just confirm that that actually gives you what you want. Start out with U being along X. So again, 1, 0. And then calculate U prime. And then I hope you will not forget that column and row vectors are treated the same way. It's equivalent, it's just a different procedure. I don't think the people on Zoom are actually doing these things.
Yeah, I'm here.
Hi. Are you actually multiplying any matrices out there? Oh, I got one yes. Okay. Is everybody happy? Can we move on? All right. Now the next distinction between treating rows and columns is an important distinction for us. I am describing fudging a bag like it starts out here and then somebody kicked it, some physics happened and now it's over here. That's the rotation we just talked about. Now we're talking about a different thing, which is more typical of the NMR problems. We change our frame of reference. Change your frame of reference. I don't move anything. I'm just changing my frame of reference. So I've got this tensor that is in the principal axis system, and it's a true tensor, but I don't want to look at it in that frame. I want to look at it in the laboratory frame. I just want to re-express it in the laboratory. I'm not moving it. I'm putting it in a different frame so that it can join the same equation as the spin operators. Changing the frame of reference. If you think about it, the coordinate system is what's moving, and the object is sitting still. We call that a passive rotation, change in perspective of the observer. And it turns out to be actually the inverse or the use of the negative angle. In other words, if I say, hey, here's this guy who's, used to be at 0 and he finally got to 15 degrees. Oh, but the thing is, I'm much faster than him, so I'm up at 30 degrees. So to me, he looks like it's a negative. Change of point of view. We didn't move the object being described. We changed the point of view. And change the point of view corresponds to look at the initial frame point of view, and then the frame you really want to be in. And this guy who never moved, it's as if he moved by the negative of the angle that the frame actually moved by. So he could either put inverse rotations or negative angles when the coordinate system is what's moving, not the molecule. So a frame transformation for a column vector would be R of minus theta on V gives you V prime. All right. So those are rotations just in a plane of a vector, 2 dimensions. Keep track of if it's column, row, keep track of if it's a frame transformation or an active motion of the object itself. So now, if we had a uniaxial object, it just allow us to ignore the rhombicity for a minute. Then in polar angles, polar coordinate system, I think I'm going to go over to the board for just 1 minute. Polar coordinate system. Need this again. You use these when you first, did geometry. You use these when you talked about orbitals and an atom. Let's just remember that instead of X, Y, and Z, we have a pole. And down here, we again have an XY plane. But when we describe an arbitrary vector, let me put my vector in black. Here's some vector V. And what properties does this vector's orientation have? It has how far am I off of the pole? Theta is the angle between the major axis and the vector. And then we can project relative to a special location in the plane we can project this vector down, like down onto the plane, and it will turn out to be not perfectly along that special axis that would have been like X in the Cartesian, so this would have been like the. It's not right along that when you project it down, but it may be off by azimuthal angle, which is usually. So if it's uniaxial, very, very important is beta or theta, or the angle down off of the pole. Very important. So an angle beta, polar angle, we're going to be calling this theta beta in our convention, takes the old z and moves it to a new z, new coordinate system, takes a polar angle, and its size has to do with this dot product. Old z dotted into new z divided by the magnitude of the two vectors. In the first and the last frames, for any frame transformation, if they have no distinction whatsoever between x and y, if they're strictly uniaxial, this is a key rotation. You move the z-axis, and that rotation, by the way, to move the z-axis from here to here, is actually, by convention, a rotation around y. So y goes into the board in my picture, and it's around y that I've moved my frames. If x and y don't make any difference at all, our frame transformation is just move old z to new z through an angle, and we can accomplish that by rotating around y in general. Now, it could be also that we have to keep track of x and y. That's a general case for us in NMR biomolecule. We have to actually keep track of x and y, means it's going to be more complicated. We have 3 angles that we have to talk about, and the everybody likes a good transportation analogy, I think. So you could ask about the nose having a pitch up, or the tail up, or the nose up. Okay. You could ask about basically turning left or turning right. And you could also have a roll of the whole object to be rolling. So there are 3 independent angles. And something that has no particular symmetry to it, you can't do with fewer angles than that. When we have 2 coordinate systems and we think x and y are different, we're going to use an angle sandwich. So the centerpiece, the most important thing that's going to happen here is to rotate around y to take old z to new z. That angle we already talked about. It's the centerpiece, it's the most important, it's the heavy lift. So in this picture, I kind of finessed the fact that I wanted to rotate around y, but I said, oh, maybe this is a little off of x, and nobody stopped me and said, wait, is it along x or is it not along? Uniaxial. I just said, okay, let's say x and y don't matter. This is the centerpiece angle. Move old z to new z. And it's all we need to do if it truly is uniaxial, because we're allowed to put it y anywhere we want. One angle, uniaxial. But if it's not uniaxial, we have to do 2 extra steps. The first thing we need to do is get ourselves lined up so it is on x. That's what I hedged. Nobody stopped. So actually line it up. So that's a preparatory angle in the way I think about it. And it's an angle around z. So step 1 is go rotate around z until you can see that your vector and the x-axis are good. Now you could fix your beta by rotating around y with the angle that you need. So you're lining up your 2 z axes. Once you've done that, You have a final question to ask. So you have brought this vector V to be in line with a new frame Z. And when you do that, how's your XY plane doing? Is it all lined up the way you want or not? You have to check it. If it's not, that's a third angle. But if so, that would be another rotation around Z to true that up. So you have a moment in the middle where you fix your x-axis. You have to line yourself up to do that action. And then you have to check how the XY planes line up afterwards. Angle sandwich. So you begin here, let's say old Z. Old Z. Okay? This is our original axis. Maybe it's the principal axis system and we want to view it in the laboratory frame. Old Z. Okay? And we're trying to go to a new axis system. It's red here. That might be like the laboratory. Okay? What we're going to do, the first thing is we need to place the y-axis correctly. So X, Y, Z is here right now. I want to rotate around Z, and I am going to move myself until I like where Y is. Because Y is my next move. That's going to be my action. So I'm going to move old Y until it comes to some new Y position. And I declare that position to be good. It's this green line here, which I call N. I'll explain why in a second. And once I get Y where I want it, that was a rotation around Z, I'm going to rotate around it. And I'm going to let it move me. Rotating around N will move old Z to new Z. And that's the most important thing that happened in that angle sandwich. But then, once I've done that, I need to think, okay, why didn't it move in that last move? So I'm still here on green. Where is it supposed to be in my coordinate system and get it there? So, special thing about N, like green vector, is that it is in both the old XY plane and in the new XY plane. It is the mutual perpendicular of those two Z's. It's the only axis that can move old Z to new Z. There's only one axis that can do that. That's what I meant when I said let's true this up so we can rotate around Y. You have old coordinate system, old XY plane, and you have new coordinate system, new XY plane. They only share one vector. That vector is what you need to use to rotate old Z and get it to move to new Z. So you see, this green N is the special thing. It's the axis that's able to take Z to the new Z. So you got to get Y there. That's your preparatory angle. Get your Y-axis where you need it. Then rotate around it through theta. And then at the end of all of that, you may need to rotate around Z one more time so that you're truly looking like the lab frame. Questions, comments?
The last rotation about first rotation is about Z.
Around Z, and locate your node plot.
And then to the beta, we
That's a rotation around N, this temporary y-axis, taking you from old Z to new Z.
yes, and that last angle is just a correction factor. We didn't make it all the way to the Y, to new Y.
Yeah, so you want to like move Y to be here and not here. If it's important. If it's important in that frame, it might not be. Like the lab frame itself, generally speaking, is uniaxial. So a lot of times we don't need it. Yeah.
There's always like 30 ways to do this rotation, but is there a reason why you just don't like rotate data? Like, is this way more algorithmic?
Tell me the alternative again.
Just like if you look at the picture you drew up there,
Mm-hmm.
you have like if you say V is reduced.
Oh, this picture.
Yeah, this
Yeah.
you just like rotate through theta and then through your azimuthal angle.
But what will I rotate around?
It's like
What axis do I rotate around?
For the first one, I guess we're on right, and then for the second one.
Well, it was okay, except that, do you remember that I said this wasn't quite on X? It would be perfect to do that if it was on X, but it isn't generally on X, and mine is a little off of X. We must rotate around the mutual perpendicular. So the preparatory angle is to get Y on that mutual perpendicular. Does that make sense now? So you usually don't get rid of that first rotation, but sometimes you can get rid of the last one. I'm just pausing to see if there are any other questions, and then I'll go on. We don't use any rotations around X. We don't need to learn how to write those. If you had a rotation around X and you wanted to do it, you'd have to make a combination of Z and Y. And you can think about that if you want or not. It's not assigned homework. How do you make a Rx out of Z's and Y's? Again, if the first and last frames have no distinction between X and Y whatsoever, you only need to do one rotation. And normally our last frame is the lab frame, and it has no distinction, so we can drop the last. Now here's the cool thing. You know how to write this. You totally know how to write this. So if we call the first rotation alpha, we said it was around Z. That's a rotation around Z, the XY plane. You just confirmed it for me. You don't even have to take my word for it. You did it. Then, you might not remember this, but the right way to write a rotation around Y is by transmuting this. Like, so it's the Y that doesn't change, so it gets 1 on the diagonal and zeros everywhere else. But those cosines and sines just get moved up one in one direction, one in X value. That's a Y rotation. And then after I do that, I have to rotate around Z through an angle gamma, alpha, beta, gamma. And we sometimes don't need this. So sometimes it's just these two. This is just me multiplying this out, in case you want to see it that way. And if you only need 2 of them, then this is your matrix. If you need all 3 for some reason. More elegant to see it expanded like the first one. All right, so back to our Hamiltonian. The CSA is written entirely in the lab frame. Now that's the same as writing it entirely in the PAS frame. I should get the same number. I don't care what frame I write it in. If I write it in the PAS frame, then I need to convert B naught and I naught with a rotation. And I'm going to use those Euler angles as being my rotation. If I write it in the lab frame, then I need to convert sigma. It's fine, you can do it either way. So I'm going to choose to move these vectors first, the lab and the lab B naught and the lab expression of the measurement vector I. I'm going to move that into the PAS. The reason I'm going to do that instead of the other choice is that then we just have to rotate the vector which we're confident with. And then we'll turn our attention to what if we wanted to rotate that tensor? What should we have done for it? That'll be later, okay? So I'm moving the vectors because they're split off and we can do them one at a time, and it's just a rank one that we're comfortable. So RLP is a rotation that moves the coordinate system from lab to PAS. There should be a passive rotation. Change coordinate system, not the vector. And it goes through an angle, and we usually call the angle capital omega, and that is equivalent to saying alpha, beta, gamma. Once again, we've reused a symbol. Sorry about that. There are some symbols that we just keep using over and over again. And I can fix it, but it wouldn't look like a textbook. So, from the lab to the PAS, it's whatever the angle is that's correct to do that passive rotation. Recall that an active rotation of a column vector is I column is R through an angle theta or omega or whatever on I original. Passive would be I in the new frame is the inverse, okay, or the negative angle. So who's a column vector here? In the way that we're writing the Hamiltonian right now, the measurement vectors. It's a column vector of operators. And so I in a PAS should be RPL on I in the lab frame. Or the inverse of LP on the lab frame. So LP is from the lab to the PAS, which is what we want to do. So you can remember that that has to be the inverse because it's a passive rotation, or you could write it this way. The rotation of the opposite. Similarly, on the bottom, and I'm sorry. Oh gosh.
See, yeah, you can see it on the TV, but I don't think it's like.
That is for the row vector B. Okay, that's what we're going to do to the row vector B. I have to learn how to operate everything in this room instead of just being helpless. So, the CSA. I'm going to leave the response tensor in a principal axis frame. I'm going to move B naught to the principal axis frame. So B naught principal axis frame is equal to this little thing in the red box. I'm going to move the measurement operator vector to the principal axis system. So that's equivalent to this whole green box. So this is an equation that's written in the principal axis system, but of course the resultant is just a scalar that needs no frame. Everybody okay with that thing? Take your time and then just tell me when you're ready to.
So even for the operators, we are not sandwiching the operator here in for the rotation. We are treating it the same as.
It's a vector of operators. And when we rotate it, we get linear combinations of those operators. So if I sit in the principal axis system, which is what I chose to do here, okay? Like that's a magnet, and I'm like this, okay? I think you're making measurements along X and Z. Like, I don't think you're measuring along Z, I think you're measuring along X and Z. That's what it said. I took a non-natural point of view to the problem, and now I have to make linear combinations of operators. Anything else? The same equation, okay? This equation here at the bottom, the one with the red box and the green box, all right? I am going to write the exact same equation and just put a different box. I'm just going to circle a different sandwich. Look at this. The CSA, you could also say it is, I take B in the lab, I in the lab, and I did a funny thing to sigma. What did I do to sigma? Sigma is a mathematical object with two indices. It has basically two different coordinate systems it's referencing, the one for the lab and the one for the perturbation and the one for the response. So if I want to rotate PAS into the lab, apparently what I need to do is operate on it twice, one for each index. And I want you to just sit with that fact for a minute. See if you have a question about it. Bilinear, you may call that. It has two indices, and it must be rotated by two applications of R. It's like a sandwich, R inverse, and then sigma and then R. Now, in this case, when we talked about moving B, it was a passive rotation from the lab to the PAS. Now, this is a passive rotation from the PAS to the lab. So if you remember when I flipped this over, I said, hey, you could talk about PAS to lab or lab to PAS. I'm going to choose to do it this way. It seems appropriate now because you're going from the PAS to the lab, and you're seeing that the way to do that is to multiply by R inverse and your original sigma, then R. Okay. From the PAS to the lab, passive frame transformation. Any questions? Any thoughts about it? All right, so sigma is a 3 by 3. It's just 9 numbers that Ruth Stark gave you. All right, R is a 3 by 3. We just worked out what it is. There's one small problem, is how do you know what beta and alpha and gamma actually are? How do you know what they actually are? I had a hint for one of them on a slide. Like, I think in order to answer that question, you have to imagine a scenario. Like, when would you be asking this question? What's going on? Let's say you're asking this question because you're doing a single crystal experiment. You would know what beta is if you know actually where the vector is in the lab. So you have to calibrate your goniometer and so on and so forth. But beta would be that expression that I had there before. You take the dot product and then you divide by the magnitude. So in order to use any of this, we need to be able to sensibly choose beta, alpha, and gamma. But we have all the apparatus we need right now to move from any frame to any frame. So in order to answer that question, I'm going to give you concrete examples. And then maybe that'll help you think about another example, or maybe each example is hard. I don't know. Just depends. Let me remind you though, these are nested frames that we're going to be using. We're not going to do one rotation. It is not PAS to the lab. That's fine for the single crystal experiment, but it's nothing to do with the biophysics we actually do today. We will have PAS and it will be dynamically averaged. Probably. Then once it's dynamically averaged, we will have to combine that interaction with another interaction. So there'll be something called a molecularly fixed frame or a crystal fixed frame. It's a place where we can add dipole and CSA and all this stuff. One frame for all the interaction. Then we have to place that crystal in the rotor. That's building the power average. So we have to say, okay, I'll place it this way. Now I pick another crystal and I place it a different way. Build up the power back. Then all of those crystals get rotated by MAS. Those are nested frames. And I know it looks like I'm comically trying to make a lot of them, but sometimes we really need all of this. The general problem needs all of this. And even it could be worse than that because the molecular fixed frame and the crystal fixed frame, you could make a distinction between them for some problems. So here's some comments about being in this kind of problem with all these nested frames. Coordinate transfer NMR are often used in a nested fashion, multiple transformations, and even some are time dependent. From the PAS, we might move to a molecular, crystal, rotor, laboratory. The first transformation is important. All the interactions are put into a common system. Rotor fixed frame, we build a power average. We said that use of a rotor frame is to account for the time dependence of the rotor as it rotates. All of the time dependence in our Hamiltonian is conveyed in a rotation. It doesn't have to be that way. You might actually change the values of sigma due to some chemical event, but normally we don't do that. In normal simulation, every time dependent, everything dynamic sits in the rotation. With all those rotations, is it hard? Do I have to really defend myself if I say I like to do the rotation the simplest, most elegant way I can find, right? And it's very inviting to make everything uniaxial. So each step looks like what we just said. Say we have 5 frame transformations. We have to do 5 of these crazy matrices, right? We talked about how we might know what to put in for alpha, beta, or gamma, and I said it depends on the context. Here's an easy one. When we move from the rotor fixed frame to the lab, which is the last transformation in the one I laid out, we know what happens to Z. It's different by the magic angle. So a rotation about the axis Y through an angle beta, which happens to be the arc cos of the square root of 1/3. We'll talk more about that later. If we talk about the crystal fixed frame going to the rotor frame, that's random numbers, literally. But there are better or worse sets of random numbers for computational efficiency. Yeah, so it depends on the context. And we'll do some work problems so you'll begin to know how do we know the angles. I like to ask that we come back to this from the PAS to the crystal fixed frame. We'll come back to this slide. I'll have a problem about it. It's in the slide deck. You're free to read it. But as far as electron, yes, please.
Are the molecule frame the same as the crystal frame, or we only need to have?
In my layout, it was the same. I'm saying that you could come up with examples where it is, but in what I have, at least. Like, what if you had 2 molecules per crystal? There's an example. There are different funny examples where it's not the same, but for me, for right now, it's the same thing. All right. So, rotate arbitrary shape in 3D angles, Rose conventions. I think this is a repeat because that happens to be where I broke for lectures last year. So I have a little repetition here. Rotate from the PAS to the lab. Simplify the calculation. We're only going to want, in simplifying this calculation, we are going to keep in mind that all we want to get out of it is the 3-3 element in the lab frame. So if there's any operation we're doing, think like a computer programmer. If there's any operation we're doing that's going to give us some other element, drop it. Drop it in advance. Don't be doing it. So what does that kind of thinking give us? Could be something funny. Even though it is not a symmetric matrix, it is not, CSA is not a symmetric matrix. We are going to pretend it is. This has to do with knowing in advance the terms that disappear in the last step. Okay, break it down to 2 different statements. CSA is not symmetric. How do we know that? Why would it be symmetric or not symmetric? Just think about it for a minute with the molecule in your mind. What's the definition of the CSA? Derivative with respect to the applied field. Derivative of the induced field with respect to the applied. So I'm saying I want to measure along Y, but I'm going to perturb along Z. That's what the definition is. Now, if it were a symmetric matrix, that would be the same as what? Perturb along Y, measure along Z would be the same as measure along Y. That's what a symmetric matrix is, right? You can flip the indices and you get the same value. So, you know, this position and this position have the same numerical value. Exactly. Is that true? On a molecule. If I perturb along Y and I measure along Z, am I guaranteed to get the same thing as perturbing along Z and measure along? No. And I can come up with lots of examples where your intuition says, no, wait. It is not a symmetric matrix. And in everything you will read in NMR, with very few exceptions, they will act like it is. What the heck? What are they doing? Let's break down an arbitrary matrix based on nothing. It's just numbers, 9 numbers, okay? Into a symmetric and an anti-symmetric component. So the symmetric component is symmetrized. On the diagonal, I need not do anything because he doesn't have a pair. But this guy had a pair up here, and I'm just going to average across the diagonal. Okay? This is the average, this is the average, that's what I call a symmetrized matrix, okay? We do this in kinetic problems, other problems. Because the symmetric matrix has some special properties that make everything easy. Now, what's the antisymmetric residual? It's like the difference between this and this. So that by construction, if I add this and this, I get that back. What is that? I take the difference between them. And also divide by 2. And I take it so that I give preference to the original value. The sign choice. Okay. So that's my symmetrized and then an anti-symmetric thing left over. And you'll see that this is equal to the same magnitude opposite sign in every case. So it's a little dipole-ish to say this. Questions, comments? That's just a decomposition. They're going to pretend it's symmetric, so they're going to work only with the symmetric one. Why? Why are they doing that? Here's why. If I want sigma 3,3, and so that is, I'm going to rotate and pull the 3,3 element. Since I know that I can decompose, and these are linear operations, I could say that's the same as calculating the symmetric one and pulling the 3,3, and then calculating the anti-symmetric one and pulling the 3,3. For an anti-symmetric matrix, the 3,3 element, any rotation, doesn't matter which rotation, the answer will be 0. That's why. That's why they're going to pretend the CSA is symmetric when it's totally unphysical to say that. So you can just symmetrize your matrix and calculate that. Now, is that going to save us any time? It's not obvious right now, but it will. It's a major deal idea, actually, and it's going to have some corollaries like that. So just get rid of anything anti-symmetric from the get-go. The form that we like to see the matrix in is a traceless diagonal form. Such a thing would never exist for the matrix that's a true matrix that has anti-symmetric character in it. Wouldn't have a traceless diagonal form. It wouldn't be summarized by just 3 numbers. It would have 9 numbers, and you need 9 numbers to say it. But no, we use 3 numbers because we believe that we only need the symmetric piece and that we can report it in the literature in its traceless diagonal form. So the 3 diagonal entries are the 3 spatial directions of the functional group. They are 3 special frequencies, and they are the max, like our turning point, and the minimum, maximum, minimum, turning point. And when you average them, you get the isotropic shift, but that's our frame. We're not using the Larmor frequency, we're using the isotropic shift to be our frame. So the average is 0, traceless symmetric. Does that make sense? I just shifted frames on you, so and introduced it mid-sentence. Right? And a rotating frame defined by the Larmor frequency, but by the isotropic shift. So we just focus in on these anisotropic. Okay? So actually, if we said we're in a frame where the isotropic shift is 0, we really only have 2 numbers, not 3. Because we have a constraint that they have to average to 0. So we can always write a traceless symmetric matrix as being delta, and then about -1/2 delta, where this one has to be corrected by with eta, and this a little bit down by eta. Okay. It's traceless, diagonal, not uniaxial. Everybody good with those 3 properties? It's not uniaxial, it's rhombic. It is traceless. It is diagonal. 2 numbers. We're down from 9 to 2. We've only got 2 numbers to work with. I think this is progress. This is real progress. So our tensor is very sparse. It's heavily, significantly sparse. And it is in a frame that conforms to the orbitals of the molecule. Let's recap. The matrix is decomposed in terms of antisymmetric, or I say asymmetric, but it's really antisymmetric. That never influences the shift, and we throw it away right away. Isotropic part, it influences the shift, but we decided to call it our reference frame. And traceless symmetric, and that is our anisotropic. Okay, so a rank 2 object always has those 3 pieces. Isotropic part is the average, so the spatial average. It's your s orbital, if you like. The asymmetric part is dipole-like in character. It's sitting in a 3 by 3, but can be written with only 1 rank if you wanted to. Just like the isotropic part could be written with no rank. And then this is what is properly only possible to write as a second rank tensor. It is a traceless symmetric. And it actually only has 2 degrees of freedom. It only has 2 parameters that are needed to describe it, delta and eta. That is basically what spherical harmonics are. It's decomposing an object described by Cartesians with a rank 2. In this case, we're just focused on rank 2. You can ask questions like this about higher ranks, and they are relevant for NMR, but we're not doing that this week. So is rank 2 information written Cartesian has to be 9 numbers. The relevant part of that, if you decompose it in this special way, 2 numbers. And it's going to help us with the rotations also, thinking this way. So 3 parts. I pull out of this 9 numbers, 3 by 3, and I can front part. Well, guess what? I don't need to rotate that. It doesn't need to be rotated. It never does anything when you rotate. I can pull out the antisymmetric part, and actually rotating it is really easy because it's vector-like. But I also already agreed we don't need it because it doesn't influence our shift. So even though those are the easy calculations, just forget it. Now we're going to rotate only the symmetric component. It is a d orbital. People always say it looks like a d orbital, but be careful. You know how when we have the p orbitals, you have an x and a y and a z, right? Remember that? And so they're Cartesian, right? And then they show you these d orbitals, and it's not like the p because they don't look like each other. Like some of them look like dumbbells, and some of them look like they have a hula hoop. Why are they all different shapes? Do you guys know the answer to that? Like, why? How come they all look the same? P, they all look the same except they're rotated. What happened to the d orbitals? That each one has a different kind of shape. Does the question make sense? P is just the same except it's facing a different axis. So I thought, you show me the D's, they'll be the same, right? They'll be an interesting, complicated shape, more complicated than the P, but they'll all look like each other except pointing in a different direction, right? I don't know about that. The way that they teach d orbitals for freshmen, some of them are actually expressed in complex notation, and some of them are expressed in Cartesian, and it's just a convention that chemists have been doing for a long time. So you could draw them differently than we do for undergraduate chemistry, and they would all look the same except for rotation. You could do that. Anyway, we have 3 parts, and we are ignoring 2 of them, and now we just have to learn to rotate just the L equals 2 component. So in order to express this with a proper nomenclature, our tensor, which up till now has been 3 by 3, 9 numbers, is now going to be given 2 indices. So we're going to pull from that 9 numbers, that 3 by 3, pieces of it. And each piece that we calculate will just be like a computation, like take that one on the upper left and add it to twice that one over, okay? Each of them will just be a computation like that, and each piece that we pull out will have 2 indices because we're dealing with a rank 2 object. The first index is angular momentum, literally. The second index is is an orientation, special orientation with respect to Z. Okay, it's the L equals 1, but which way is it pointing? That's N. Okay. So L for us at this point, it can only be 0 to 2 because we started with a 2. It started with a 2 at second rank. And L can be 0 asymmetric, isotropic asymmetric, or what we really need to deal with here, trace asymmetric. M ranges, as you know, from chemistry, but it's going to be the same thing here, from minus L to L. So how many objects do we have? We have 0, 0, 1, 0, 1 minus 1, 1, 1, 2 minus 2, 2 minus 1, 2, 0, 2, 1, 2, 2. We started with 9 numbers, we have 9 numbers. That's normal. So it's a frame transformation, it's a new set of coordinates, and it's going to be especially good for writing second rank tensors and rotations in their simplest possible form. If I rotate something, you were told this last week, I'm just going to say it again because it's really important to remember. If I rotate something, I cannot change L. You believe that? Like I pull a component from my matrix and I rotate it. If it looks like it's L equals 0 before I rotate it, it has to look like L equals 0 when I'm done with it. This is a frame transfer. That's all it is.
Symmetry.
Yeah. And the L value is a real property of the thing. I can't change frames and make an S orbital look like a D orbital, can I? No. All right, so rotations preserve L, but they mix the various M homologs. So I can turn a p orbital into a px orbital into a py orbital by choosing a different frame to look at it from. But I cannot turn that p orbital into p orbital. So this is going to be a very restricted as to what we have to calculate. It's going to be much simpler. So what are these 9 things? Well, M00, we already said what it is. Take the average of the diagonal. And the matrix does not have to be traceless or symmetric or anything in particular to just be able to take that average. I can take that average on any 9 numbers. And you will see that whatever you do to that matrix, whether you leave the antisymmetric part in or you take it out or whatever you want to do, that will be invariant. The trace is a trace. That's why they teach it to you now in linear algebra. It's one of the nice axiomic things. All right. L equals 1, but M sub L or M is 0. Well, that's a calculation that you do where, but what I mean by this is that you're going to dot that onto your actual matrix. So I don't do anything with this element, I don't do anything with it, but I take this one full strength, this one, and when I take that dot product, I add the 3 non-zero entrants, right? Like I have got 2 vectors, I'm dotting to, it's an inner product of 2 rank 2 objects to get a rank 0 object. M10 can be defined the same way. I need to pull these 2 elements, but one of them gets multiplied by -1. So each of these, after I'm done with that, I'll have a number, which is like an amplitude of that component within the matrix. How much of this character do I have? How much P character do I have? How much S character do I have? Okay, a matrix could have 0 for this one, but a large number for this one. So this is like a basis set that we're pulling the characteristics out of the matrix. And we're allowed to use imaginary numbers to make these calculations. So 9 linearly independent orthogonal objects span the space for these 3 by 3 matrices. But instead of organizing them according to their Cartesian characteristics, we are organizing them according to their angular momentum. How much S character, how much P character, how much D character. There is such a thing as an eigenoperator of RZ. So rotating a thing by RZ returns the same thing, but maybe with a multiplicative factor out in front. Remember, eigenvalues, you take an operator and you operate on an object and you get the same object back, maybe times something. Well, an eigenoperator of RZ means that I rotate that thing. I have this thing, I rotate by Z, and I always get the same thing back times a base factor or a multiplicator. Except that rotations, we like to see that it's the same size, so that multiplicative factor will be more like a base factor. We don't like to see things getting bigger or smaller. Now, why am I mentioning eigenoperators here? Well, first of all, if you knew that your object was an eigenoperator, you would know that rotating it was going to be easy peasy, like nothing to do. So that's kind of something we want in these Euler angle calculations. We want some of these operations to be easy. And do you remember our angle sandwich? We had 2 z operations and only 1 y operation, right? So I love the z. I know sometimes there's 1 z and 1 y, I know, but if I want one of them to be easier, I'd like the z to be easy. So what we're going to do, within the L equals 2 set, we have different ways we could decompose it, that we could define, you know, what are the 5 pieces of L equals 2. I want those things to be eigenoperators of RZ. And that is the special thing about M sub L. We're just calling it M here, but it's laid out that way, that the Z, like each of them is really easy to rotate around Z. You don't need to do a calculation, it's done by inspection. So we want to use this kind of a system, both for the spatial and the spin interactions. We want to use this spherical harmonic, Wigner rotations, with Rose convention Euler angles. We want to use that for spin and spatial. Now, converting a Cartesian matrix to the spherical harmonic. You had 9 totally arbitrary numbers in a 3 by 3.
And I think there are people waiting.
What's that?
I said there are people waiting for you.
Oh, okay. They need a room. Is that what you think?
Yeah, you know, we have until 3:30 and then.
Oh, I'm so sorry. So this is a great place to stop. I just said that if you have an arbitrary matrix, you can turn it into a different basis set. And this is a good summary slide. This is it. This is like, these are in the spherical harmonic. This is where you started as Cartesian. You can always turn it into that. And what we'll get starting tomorrow is how do you actually write a rotation with it? Okay, so I decompose, I go to all this trouble, I rewrite my Cartesian. How am I going to actually work? You're saying it's so easy, let's do it. Okay. Thank you. Sorry that we're not going to take a minute for questions, but please bring your questions next time. Tomorrow at 1.